Hello, today I will present the first part of section 13.4, Increments and Differentials. Let's start with some simple single variable calculus, so this is just BC. Let's have a function y equals f of x, and let's say it's a parabola. So this is its graph. And then this is x and y. Let's choose a point x, y on this curve, x, y, and another point x plus delta x, y plus delta y, where the distance along the x-axis is delta x, and the distance along the y-axis is delta y. So delta x and delta y are sizable changes in x and y, so like 0.1 or 0.01, and these are known as increments. And we know that the derivative of a function is equal to the slope of the tangent line at that point. So let's draw the tangent line at xy. So the distance between f of x and this point is called dy. And we can use this point to approximate the value of the actual function at this new point. And we do this by saying delta y equals f of x plus delta x is approximately equal to dy. And dy just equals the derivative of the function at our original point times the change in x. And this is an equality because these are differentials. These are infinitely small changes in x and y. So also note that in single variable calculus, f of x equals y, you only have a single input, a single independent variable, which gets turned into a single dependent variable. So now let's see how this translates into a function of two variables. So in a function of two variables, you would have z equals f of x and y. Now you have two independent variables, but still a single dependent variable. This makes the concept of increments and differentials slightly more complex. So let's take the function, let's say the function is some sort of paraboloid. So it would look something like this. So now let's say we start on a point xy, take f of xy, so now we have a point f xyz. And now we want to see how much the change in z is when we change x by a certain amount, delta x, and y by a certain amount, delta y, to get to delta z. So let's think about this for a second. Let's consider just the graphs of the xz and yz traces for now. So the xz trace will be a parabola, and the yz trace will also be a parabola. And let's have this point and this point. So now when we change x by delta x and y by delta y, can we still say that delta z, which equals f of x plus delta x, y plus delta y, minus f of x and y, can we still say that delta z equals, for example, dz over dx times delta x? No, of course not. And because in multivariable calculus, you can't take just the derivative with respect to one of the variables. You have to take the partial derivative. And so, what about considering this quantity? So, what would this look like? In single variable, this would just be dy equals dy over dx times dx, and this would be your linear approximation. But in a function of two variables, you can't just deal with the variable x, you also have to deal with the variable y. So we have the same quantity here, partial z over partial y dy, and what the total differential tells us is that if you add up these two quantities, then you get the then you approximate the change in the function as you move x and y by a certain increment. So this is the total differential. But why is the total differential formula so simple? Can't we're adding two quantities on two different axes. Doesn't it make sense if we try to square something or something like that, like in the Pythagorean theorem, for example? Well, let's interpret this geometrically and see what it looks like. Let's say you have a function of two variables and we're trying to approximate the delta z as the function as x varies along delta x, and the change in y is delta y, and this is delta z. So we know the partial derivative partial derivative with respect to x and with respect to y. And so let's try to represent these quantities geometrically. So first let's do the x-axis. So this is the tangent line on the xz plane, and we are intersecting it with this plane that's defined by this x value. So it intersects at this point, and we have this quantity as being equal to partial z over partial x dx. And now we can do the same thing with delta y. and we get another similar quantity. So let's see why we are able to add these to get the total differential. So here I have removed the original function, and we are just looking at the differentials here, which actually construct a parallelogram. So this is dx, and this is dy. These are the side lengths of the parallelogram. But notice that this these lengths are equal. This is also dx, and these lengths are also equal because it's a parallelogram. Now, we know that this length is can be considered dz1, or the partial derivative of z with respect to x times dx. And this length is dz2, which is the partial derivative of z with respect to y times dy. So how is it that when we add these together, we get dz? Well, let's see. We have dx here, and this actually also represents the same change in z when you move along the x-axis. So actually, not only is this dz1, but this value here is also dz1. And then we know that this is dz2, so isn't this also dz2? So we have shown that by adding dz1 and dz2, we get dz, which is what we want. And that's the geometric interpretation. Okay. Finally, I want us to solve a problem, but before we solve a problem, I need to talk about approximations. And these are differentials, so this is an equality. However, in the real world, we're not dealing with differentials usually. We're dealing with incrementals, a small but significant change in in a value. So we say that dz approximates delta z. Approximates. We say that dz approximates delta z. And this allows us to solve a lot of functions where we want to approximate error, approximate the change in a function when you change the input variables, or approximate the value of a function from a point where it's easy to find the function value. So let's do a hard example and see how to solve it. So this will be in the problem solving section of the book, and number 16. So problem solving chapter 13, number 16. So let's say we have a point in polar coordinates, r theta equals 5 comma pi over 18. However, they say that when measuring the dimensions of this point, we might have a maximum error in r of plus or minus 0.05, and a maximum error in theta also of plus or minus theta, plus or minus 0.05. So, the question is asking, when converting from polar coordinates to rectangular coordinates, so when converting from polar coordinates to rectangular coordinates, does the accuracy of x depend more on the accuracy in r or theta, and likewise for y? So let's draw this out first. So we have pi over 18, which is quite small. That's pi 18. So that's 10 degrees. and then r is 5, and this is x and y. So we know the convergence, x equals r cosine theta and y equals r sine theta. And notice that x and y are both functions of two variables. So when we vary theta by 0.05 degrees, we might get something like this. 0.05 radians, sorry about that. We may get something like this, or something like this. And then this will be our new delta x and delta y. This will be our new x and y. When we vary r, we get something like this, and something like this. So immediately, you can kind of tell which variable will have a bigger impact on which variable. For example, it seems that when you change theta, it affects the change in y more than when you change r. But let's see if this is actually true. So part A wants us to solve whether x relies more on the accuracy of r or theta, so let's do that. We want to find the error in x, which is approximated by the total differential. And let's plug in values of r and theta, so based on the specific situation. So here, the partial derivative of x with respect to r is just cosine theta. And then, since we're dealing with delta r and delta theta, we can also write dr and d theta as delta r and delta theta here. And this is simply what we can do for linear approximation. And let's take the partial derivative of x with respect to theta. So this is negative r sine theta times delta theta. And now we know r theta, delta theta, so we just have to plug in cosine pi over 18 times plus or minus 0.05 minus 5 times sine pi over 18 times plus or minus 0.05. And we want these to be the same sign to find the maximum error. So I'm just going to flip this to become minus plus. So that way when you multiply by a negative sign, it becomes plus or minus, and then these errors would add together. So when we do that calculation, we're getting dx equals 0.98 times plus or minus 0.05. This is coming from delta r, and plus 0.86 times plus or minus 0.05. This is coming from delta theta. So since the contribution from delta r is greater than the contribution from delta theta, we can say that the accuracy in x relies more on the accuracy in r than the accuracy in theta. So that's the first part of our problem, and it's also supported by what we see in the diagram. And finally, let's do the same thing for y. So the error in y can be approximated by dy, which equals the partial with respect to r. And we can obviously see that the contribution from theta's error is much greater than that of r's error. Therefore, the accuracy of y relies more on the accuracy of theta than the accuracy of r. So that is the total differential, and thank you for listening.